It's just weird. Yeah, I am live, right? I think now I'm live. That's good. Anyway, it's now 9, so without further ado, let's get started. So basically, huge update today from Google's end. I managed to reset the password. I managed to reset password to my Google account, my old Google account. So now, hi Vizzy. Thanks for joining the stream. Um, so I managed to reset the password for my Google account. So I now reclaim my Gmail, and I updated all the security settings, the recovery stuff, the two-step verification. Oh, hi, wow, 5 people already. That's crazy. Yeah, so I'm actually very excited today because I managed to reset the password of my Google account, which means I can receive emails as usual. Um, I still don't have access to the YouTube channel yet because the channel right now is terminated, right? And I filed a appeal. Before that, I wasn't able to do so because to file an appeal, you need to be able to log into your Google account, which I wasn't. So now that appeal has been filed, and I'm pretty sure they were going to restore it as soon as possible on their end in a couple of days, I suppose, because they already confirmed that my account was compromised. Um, so there's that. So we're very optimistic right now to getting the old channel back. It turns out to be not too, hopefully not too much of an expensive lesson, okay, but still it was very scary. So once again, be very careful, guys. Phishing attacks can be anywhere, um, so be very careful. That's the bottom line here. It could have gone so much worse. Okay, but I mean, well, still, I hope not only I get my old channel back, all the stats, all the videos are still there. The subs are there, the views are there. You know, um, I hope this is not going to be a, too big of a setback. Right? That special Twitter handle was the secret ticket to success. Exactly. And you know what? That was surprisingly um, responsive, I would say. Team YouTube on X was surprisingly responsive. Um, to be honest, I wasn't even expecting much, as I said yesterday. Because, like, I mean, I have nearly 20K subs, but that's still a small fish in the big sea called YouTube, right? Like even if the channel is gone forever, why would they care that much, right? I was kind of depressed and cynical, and I was thinking that way. I didn't expect them to react so quickly. Anyway, so hopefully everything is gonna be normal now. Not now, but in a few days. Okay, so that's the update when it comes to restoration. And so you guys might have sound like it's just going well as possibly can in terms exactly it went way smoother than I expected. I thought the channel, this is the end, because I when I posted the first video on the 2.0 channel, I was like, I don't even know if they're able to restore it, right? To confirm the hack, maybe the hackers deleted everything. Then what the hell can Google do, right? But perhaps things are not that bad. But anyway, we'll see it when everything gets restored. Okay. Anyway, so I was I was talking about there's an alternative schedule I just planned. Basically, that's morning on my end, Eastern Standard Time at 8 a.m. So this way, people in different time zones can have it. Did they fool around in your email? I checked. Not no. They fool around. I checked my email. Doesn't seem to be okay. So yeah, they just changed the recovery email and stuff. And I don't know, like, so yeah. I mean, as far as I can tell, nothing abnormal on my Gmail account. Okay, other than it was compromised. Probably my YouTube channel was their prime target. So there's that. Anyway, I was talking about the alternative streaming schedule. Basically, early in the morning. I mean, not super early, but 8 a.m. in the morning for me on my end. This way, Wonderbar. I know, right? It could have been much worse because what if they impersonate me and send emails to my acquaintances and my colleagues and destroy my reputation and things like that, right? Because yeah, you just never knew. I honestly, it felt like a complete disaster when it happened on Monday. Like, I don't even know if any of my stuff online is safe anymore. But still, let's not get too carried away. I will not get too carried away. I have been communicating with people that I can just recall that something is terribly wrong. Did you get your email back? Yes, I did get my email back. I was talking about it. I did get my email back, so I was able to log in. I was given a special portal to reset my email because all the automated channels fail, right? Yeah, I did get my email. Now I have my email. And yes, we're here to learn math. Sorry about that. Okay. Anyway, so yeah, just long story short, tomorrow's morning is going to be me starting my first serious attempt at abstract algebra. Okay. I'm down to the nooks and crannies, not just like higher level stuff. Okay. So that will be a first on the channel because I used to talk about things that I'm relatively familiar or at least have a first acquaintance with them. Okay, in a like a serious acquaintance, I might get rusty, but I either have done research in that field or taken a formal course in that. Everything I previously did on my old channel was like that. I rarely talk about anything that I'm not familiar with because at the time I was sort of afraid of embarrassing myself. What if I say something wrong, right? Um, but I figured that's not entirely a fair experience, even though that's perhaps, you know, use my is perhaps that's the best way to use my knowledge, but perhaps not the best way to help beginners to get a full picture. Vizzy says once you get your email, you can message people that your email got hacked. Yes, I have with people who have email communication with, I typically have alternative lines of communication. I already informed those people on the first day. Like just don't listen to anything that comes from that email. So that's basically, yeah. Thanks, Vizzy. So yeah, I was thinking perhaps if I only do stuff that I'm familiar with, right? That would not give a beginner a glimpse of how studying mathematics is about. Because I certainly, because let's say this is linear algebra, this is Sheldon Axler's linear algebra. I mean, I'm not going to say if if you pull out any result, I will be able to prove it like right away. Not like that. But I'm familiar with over, at least I would say 90% of this stuff. That's not an exaggeration. I might be a little bit rusty when it comes to certain topics. For example, let's say, well, whatever. But you know what I mean. It's not like I'm starting from scratch, right? So I know what to expect. I know what results are important, even though I might not be able to prove them on the spot. And that's not a fair picture for a beginner, right? So if a beginner sees themselves not as going as fast as the pace I'm doing during the stream, they were like, okay, I'm not really competent enough. That's totally unfair because I did most of the stuff before, right? So the idea is for me to start a new field which I'm unfamiliar with, which I picked abstract algebra, like a third year abstract algebra, as the candidate for that subject, right? And the notes is in the notes. I mean, it's free, it's online, and I use that note. So when you guys watch the stream, you can actually check the notes yourself, right? So this way, I would say this way we are. I think because I always say I consider my viewers my peers, not their instructors. Okay, so I've learned a lot from my viewers, and I just hope some of my viewers learn from me as well. It's a two-way street. There's definite value in showing unpolished in the field where, yeah, exactly. That's the idea. I mean, I will show polished videos where everything is like well thought out because I don't want waste people time, right? But on the other end, I think it's good to normalize friction because sometimes when we say math is beautiful, it can only be experienced once you went through the struggle, in my opinion. Sometimes that beauty can only be experienced once you went through that struggle. Like all your previous 10 attempts of a proof went to a dead end. And just that one trick that you finally figure out, like how beautiful is that? I don't think you'll ever forget that in your life, right? So that's the idea. Like I would like to normalize the experience of pondering. Like it's not a failure. It's not a failure. It's a normal part of mathematics, right? So that's the idea. So this is not a PR department for math, okay? I just put it that way. This channel right here, this little corner of the internet is not a PR department of math, if you know what I mean. It's not saying, it's not like how mommy would put medicine in a child's candy. So this way the medicine gets easier to be taken, right? Math is beautiful and painful at the same time. I mean, there's I don't know how else I should put it. It's just the way it is. And I think because if you read a textbook, right, like Baby Rudin, everything is super polished, and you just sit in there, wonder like how on earth someone would ever come up with such a proof. Then this creates a massive psychological gap between the reader and the author. Of course, the author didn't write the book to make themselves look smart, right? They're just economizing, right? They have requirements from the publisher, right? You can't just keep rambling like I'm doing here, right? You have to put enough information within the limited space, right? That's the requirements of publishing, which is a separate topic. But still, what gets shown is often not exactly the same as the actual effort that goes behind it, right? So that's the idea. Anyway, all right. So let's just get started with the linear algebra. All right. So yesterday we attempted the topic of polar decomposition. Right. So the polar decomposition is for every operator in LV, where V is a complex inner product space. Right? V is a complex inner product space, and the idea is to write an operator T in this form. Okay, in this form. So we want to write T equals S times the square root of T star T. Here, the square root of T star T, this refers to the unique positive square root of a positive operator. And to understand the unique positive square root, we got to do a few things, which turned out to be what we end up doing most of the stream yesterday, just to understand what it means to take a square root, to take the positive square root of a positive operator. What does that even mean, right? And we managed to prove, I mean, we didn't manage, we managed to go through the proof and rewritten the proof ourselves in our own words on why a positive square root exists and why it is unique, right? So I only became aware of this weakness of my knowledge thanks to a problem submitted by Vizzy a week ago. In my attempt, I was, by the way, the problem Vizzy submitted was in terms of matrices, right? And in Axler's book is in terms of abstract vector spaces, which is not a huge abstraction, okay? But the bottom line is during a week earlier in the problem session a week earlier on the old channel, I was able to prove existence, but I couldn't prove uniqueness. You see, this is the uniqueness part where I couldn't quite nail down. At the time, I was following the standard process of showing uniqueness. Right? You suppose there are two such objects, right? Two such square roots, and you want to show that two are equal. So I set up the uniqueness proof this way, and I couldn't proceed. Right? Indeed, this is perhaps the most common way to prove uniqueness, but it doesn't work. So you try to manipulate these conditions, d1 squared equals d2 squared equals c. I cannot deduce d1 equals d2. What Axler did, and we rewritten in our own words, follows a different idea. So this is not just a generic uniqueness proof. This is the proof of a uniqueness of a linear operator. Remember, R is a linear operator, or in the problem, in Vizzy's problem's case, a matrix. Right? So how do we show certain linear operator is unique, right? So we know this R, the unique positive square root, satisfies a certain property. How do we show this is unique? Well, there is something that can be said about uniqueness of linear operator. Basically, if a linear operator gives an unambiguous result on a basis, right? That's called the linear map lemma. If that's the case, then the linear map is uniquely determined. This is something that is only true for linear map. So linear maps have this nice property, which I refer to as the data compression principle. Right? So what does that mean? A linear map is a finite dimensional object. So that means, if roughly speaking, to store information, to fully characterize, to fully capture the information about a linear map, you only need finite pieces of information. Because in general, a function is a pretty complicated thing. a nonlinear function is a pretty complicated thing. But for linear maps, if you specify a basis for the domain, v1 all the way to vn, and if their images are completely fixed, then the linear map itself is fixed. So thanks to this data compression principle, right, you just need what the linear map does to each of the basis vector. If that's already something we know, then the linear map is unique. So that's the key to the uniqueness, which I didn't think about in, well, a week earlier, right? So when we stuck about a problem, it's always worth doing something. That is, when we eventually figure out or look at the solution, in my case, it's worth going back to the original attempt and see where do things got stuck. So I was trying to follow the standard uniqueness proof template, and it gave me nowhere. Right? And also in the part 3, there's also the uniqueness part, which I also did not nail. Right? I did the existence part. By the way, part 3 is the polar decomposition. I recognized this is a polar decomposition, so and I vaguely remember there's a section in Algebra that talks about it. So that's why we spent the whole night last night trying to understand this stuff. Okay, so yeah, that's the reflection. I think it's worth it. All right. So let's just quickly go over the polar decomposition. Okay. And I'll do a first reading, and then we will pay attention and do the auditing. Okay. Recall our discussion before 7.54. 7.54 is something we put in our notes yesterday. Okay. Just to recap, 7.54 that's the result. 7.54 says eigenvalues of unitary operators have absolute value 1. Right? So that's the analogy between complex number z with z absolute value equals 1 and unitary operators. Continuing with this analogy, note that every complex number z except 0 can be written in the form of z equals z over the absolute value times the absolute value. Right? That's the factorization of complex numbers, completely trivial. Right? So we're going to rewrite the absolute value, the second z absolute value, as the square root of z bar z. Okay? It's just a different way to rewrite, the absolute value of z. Our analogy leads us to guess that every operator t in LV can be written as a unitary operator times the square root of t star t. Right? So basically, this is a scalar equation, the square root of z bar z. That's the scalar equation. And we're just going to replace z by t and the conjugate by the conjugate transpose. So this way multiplication makes sense. That guess is indeed correct. Right? The corresponding result is called the polar decomposition, which gives a beautiful description of an arbitrary operator on V. Note that if t is in LV, then t star t is a positive operator, as shown in 7.64a. Let's recall what this means. What this means, right? A positive operator. We did that proof yesterday, right? We didn't. We actually, the notes stopped here, right? Let's finish that up. Actually, by the way, can we prove that ourselves? It's a good exercise, by the way. Proof. Let's do that. This is the end of yesterday's notes. Okay, let's prove that if t, if t is in L from V to W, then t star t is a positive operator on V. Okay, what do we need to show? If we want to show A, what do we need to show? Well, let's recall the definition. A positive operator needs to be first self-adjoint and second satisfy an inequality. Right? So let's first check the self-adjointness. T star T is self-adjoint. Visi, if you're, or anybody else for that matter, if you're trying to pick up the fundamentals of proof writing, the first line of thought when it comes to proof is, what's the relevant definition? Right? If the positive operator has two requirements, we need to show those two requirements are satisfied. T star T is self-adjoint. So this is really easy. We just take the conjugate transpose of T star T and show it's actually T star T itself. It's just a straightforward computation. All right, use the property of the star operator. You get T star T back. Okay, so that's done. So this is self-adjoint. And another requirement for positive operator is as such. It says for any vector little v in big V, the inner product between T star T V and V is non-negative. Right? So that's the definition. Let's go back, because if I just say it verbally, it might not be the most clear. So yeah, so yesterday we took this definition down. Right. An operator T is positive if it's self-adjoint and this inequality holds. And this inequality is what we call a universally quantified statement. It sounds complicated. It basically just means something that is true for all elements in a set. This is called a universally quantified statement. Right? Everybody must have seen the inverted big A as the for all quantifier, right? So when we do proofs on universally quantified statement, what do? We always start, with no exception, we always start with the word let V in big V. That's actually an abbreviation. What we're really saying by writing let V in big V is that we pick an arbitrary vector little v in big V. That choice is arbitrary but is now fixed. Okay? And then whatever property we deduce regarding that particular v must hold for every little v in big V, since v is arbitrarily chosen. Right? So that's the template for proving a universally quantified statement. So let's proceed. Okay? Okay. So let little v in big V. Okay, so now we need to check the inequality, which is the inner product between T star T V and V is greater or equal to 0. So how do we proceed? Well, we did a trick yesterday regarding this sort of expression, is that we wish to move the first operator to the second position. And that's in the definition of adjoint. So by the definition of adjoint, this gives us TV. I'm moving the first T star to the second position. And by doing that, I need to take the conjugate transpose. So that's T star star V, which is of course TV again. Right. So that's the result, and the inner product between TV and TV is non-negative by the inner product axiom. So yeah. Okay. So that's done. Or we can write a conclusion. Therefore, T star TV and V inner product is always greater or equal to 0.
for all in V and big V. All right. So this proves that T star T is indeed a positive operator. Okay, 7.64a. Going back to Axler, this is what we did. Okay, thus the operator square root of T star T makes sense. Indeed, this notation is well defined for a positive operator. Okay, and it's well defined as a positive operator on V. Okay, now we can proceed. The polar decomposition that we're about to state and prove states that for every operator on V, that every operator on V is the product of a unitary operator and a positive operator. Thus, we can write an arbitrary operator on V as the product of two nice operators, each of which comes from a class that we can completely describe and that we understand reasonably well. The unitary operators are described in 7.55 if F equals C, and the positive operators are described by real and complex spectral theorems. Okay, specifically, consider the case F equals C, and suppose T equals to S times the square root of T star T is a polar decomposition of an operator T in LV, where S is a unitary operator. Okay, S is a unitary. S is unitary. Remember what this means. Unitary operator is an isometry. Is an invertible isometry. Okay, and we have a bunch of equivalent characterization. 7.53. That's unitary operator. Okay. Then there is a orthonormal basis of V with respect to which S has a diagonal matrix. Why is that? So basically this says S is orthogonally diagonalizable. Which theorem guarantees that? It's the spectral theorem. No, it's the spectral theorem, because the spectral theorem, let's revisit the spectral theorem. The spectral theorem is somewhere earlier, I believe, because we use the spectral theorem to prove existence and uniqueness of the square root. Spectral theorem, the following are equivalent. T is in LV. The underlying field is the complex number. T is normal. And T has a diagonal matrix with respect to some orthonormal basis. And V has orthonormal basis consisting of eigenvectors of T. So these are all equivalent conditions. Right? So here we're dealing with a unitary operator S. A unitary operator is normal. Can we check that? Well, if S is unitary, right? If S is unitary, we have one of the characterizations of unitary operator. There we go. Right here. Here. S star equals S equals SS star. So this equation here, the first equality, means that if S is unitary, then S is normal. Therefore, by the spectral theorem, it is orthogonally diagonalizable. So this sentence is perfectly valid. Right? Then there is an orthonormal basis of V with respect to which S has a diagonal matrix. And there is an orthonormal basis of V with respect to which, we didn't read that part. And there's a orthonormal basis of V. Hang on, this is a different orthonormal basis, or is it the same? Okay, starting here, then there is an orthonormal basis of V with respect to which S has a diagonal matrix. Right? That's applying the spectral theorem to S, which we just justified. Okay, and the second part of the sentence says, and there is an orthonormal basis of V with respect to which the square root of t star t has a diagonal matrix. Okay, it doesn't say these two orthogonal bases are the same, right? It doesn't say. But here there's a warning that says there may not exist an orthogonal basis that simultaneously puts the matrices of both S and the square root of t star t into these nice diagonal forms. Yeah, that was what I was thinking about. S may require one orthogonal basis, and t star t, square root of t star t, may require different orthogonal basis. That's totally reasonable. They don't have to be a priori. They don't have to be a priori the same orthogonal basis. Okay. Anyway, by the way, the second sentence, let's try to justify that. Why there exists an orthogonal basis of V with respect to which the square root of t star t has a diagonal matrix. Why is that? Well, I guess we're trying to apply the spectral theorem to the square root of t star t. Can that be applied? What can we say about the square root of a positive, the unique positive square root of a positive operator? Well, we have a bunch of results yesterday. I think it's here. In the existence part, there's a bunch of equivalent conditions. T has a positive square root. So we've shown that t star t, okay, we just shown that here, that t star t is positive. Right, and therefore, hang on, here, t star t is positive. And by our existence theorem of square roots yesterday, right, it has a positive square root, and by the uniqueness is the positive square root is actually unique. So the positive square root is a positive matrix. Sorry, it's a positive operator. I always say matrix, but here everything is an operator. Okay, so the positive square root, trivially, is a positive operator. And a positive operator, by definition, is self-adjoint. If it's self-adjoint, then it's normal. If it's normal, then it can be orthogonally diagonalized. So that's the reason. Okay, so that's the reason. So basically, we're indeed applying the spectral theorem to the square root of t star t. By the virtue of being a positive square root, it is positive, which means it's self-adjoint, which means it's normal, and therefore can be orthogonally diagonalized. The audit is complete. Okay, on this sentence. All right, so let's go. However, still assuming that f equals c, if t is normal, then an orthonormal basis of V can be chosen such that, if t is normal, did we make that assumption earlier? No, we didn't, no? Here, t isn't arbitrary, right? Because here we're expressing t is just an arbitrary operator in LB. But in this paragraph, we're assuming if t is normal, then an orthonormal basis of V can be chosen such that both S and the square root of t star t have diagonal matrices with respect to this basis. So that's pretty cool, right? In the previous paragraph, we just mentioned, even though S and the square root of t star t are individually orthogonally diagonalizable, the orthonormal basis that diagonalizes, the orthonormal basis, plural, okay, that diagonalize those two operators may not be the same. And as it turns out, this exercise 31 tells us if t is normal, then they can be simultaneously diagonalized. Isn't that pretty cool? Okay, so this is something we wish to prove. The converse is also true. The converse is true. So what does the converse say? If t is in LV and t equals s times the square root of t star t for some unitary operator s is in LV such that s and the square root of t star t both have diagonal matrices with respect to the same orthonormal basis of V, then t is normal. Okay, so it goes both ways. Okay, so something that needs to be shown. This holds because t, okay, this holds. So this is, I guess this is the justification for the converse. Let's read that. This holds because t then has diagonal matrices with respect to the same orthonormal basis. Hang on. T has a diagonal matrix with respect to the same orthonormal basis. Which implies that t is normal. I'm not quite sure where this comes from. First of all, I'm not quite sure about this part. Okay, so big question marks here in this paragraph. But let's just, for the time being, assume that, okay, this is a big result. Right? This is a big result. So if you have the polar decomposition, which we haven't shown existence or uniqueness or whatever, we haven't done that yet. But if in the polar decomposition, S and the square root of t star t are simultaneously orthogonally diagonalizable. Gosh, that's hard to say. Simultaneously orthogonally diagonalizable. If that's the case, then t is normal. And in fact, that's a sufficient and necessary condition for t being normal. Okay, so big question mark here. We need to revisit this paragraph. But here, for now, let's just show the polar decomposition. The polar decomposition below is valid on both real and complex inner product spaces, and for all operators on those spaces. Hang on. What does that mean? If t is, let's say, a real operator, if V is a real inner product space, then transpose, the star would just be transpose. And a unitary operator becomes an orthogonal operator or orthogonal matrix or whatever. I'll be actually using the matrix and operator interchangeably. So anyway, that's the statement of polar decomposition. It says, suppose T is in LV, this is an arbitrary operator. Then there exists a unitary operator, S is in LV, such that T equals S times the square root of T star T. Now, it says unique. Sorry, it didn't say uniqueness, no? It didn't say. It didn't say that the polar decomposition is unique, which is quite interesting. Because we know that T star T square root is unique. This is, otherwise it wouldn't be a notation. There's only one such matrix. But here it only says S exists. It doesn't say S is unique. I wonder if we can say uniqueness, huh? So let's temporarily not look at this proof and see if Axel has anything else to say about this S. No, nothing. Nothing. It didn't say whether this is unique, which is a little bit surprising. I don't know whether S is unique or not, because in the analogy, in the complex number analogy, if Z is non-zero, then this Z over Z bar, not Z bar, Z over Z modulus, this is unique. That's the unit length complex number in the same direction as Z. Both the direction and the length are unique. And here we know that T star T square root is unique given T. Right, but it doesn't say that S is unique, huh? And S actually should be unique. It should be, it's just not in the theorem. Because in Vizzi's problem, we need to show uniqueness. In Vizzi's problem, we're dealing with matrices, potato, potato. I mean, the proof should be essentially the same. Here we're dealing with a real square matrix. It's non-singular. We want to show that there exists unique. Oh, in Axler it didn't say non-singular. Perhaps that's the reason. Perhaps that's the reason. So in general, if let's say F is just arbitrary square matrix, then you would have this decomposition, but we don't know about the uniqueness. Okay, but I mean that's just an educated guess. But perhaps, actually, I think that's actually the case. The educated guess would be if F is non-singular, then the polar decomposition is unique, just like in the case of complex numbers. However, if F is singular, then this decomposition might not be unique. That's why we say nothing about uniqueness in the polar decomposition theorem. Okay, so that's my educated guess. And after this result, that's pretty much marks the end of Axler's exposition on polar decomposition. Okay, so now let's go over this proof. Okay, so but before we do that, okay, let's just bear in mind we need to understand this proof, rewrite it in our own word, and there are two things that's left to be done. First is regarding the uniqueness, because that's directly linked to Vizzi's problem. Let's figure that out first. Okay, so let's prove like a part 2 of polar decomposition. If T is invertible, then S is unique. We want to show that. If S is unique, hang on. Yeah, we want to show uniqueness after anyway, assuming that T is invertible. We want to do that, and if time permitted, we will do this exercise here. The simultaneous diagonalizability of both S and the square root of T star T. How about that? Okay, let's read the proof here. Okay, so this is a existence proof. This is the existence statement, right? So to do an existence proof, we need to actually exhibit such a unitary operator. That's typically how existence proof goes. Existence proof has two general strategies. You either exhibit an object that satisfies the required property, or you would assume that such an object does not exist, which leads to a contradiction. Here it seems like we are defining S. So that's the constructive approach. Okay, so here it says, let S1 to Sm be the positive singular values of T. Wow, this is singular value decomposition, huh? Indeed, this section is 7F is the application of singular value decomposition. I guess we need to review this. Otherwise, we can't follow this proof. Okay, let S1 to Sm be the positive singular values of T, and let E1 all the way to Em and F1 all the way to Fm be orthonormal lists. It just say list, it doesn't say basis, in V such that TV equals this. Looks like we have to review SVD, huh? Because this looks like SVD. Let's do that. Going back to singular value decomposition, after all, this is the application of singular value decomposition. Okay. SVD. First, we need a definition of singular values. And SVD in of in operator form. Hang on. Yeah, this is SVD. See, this is the exact statement we just read. TV equals blah, blah, blah. It's the same form. Okay, that's good to know. Definition of singular values. I'm not going to dwell too much on the proof of singular value decomposition. I'm just going to, because the main goal is to understand polar decomposition, right? We're just going to assume SVD today. And I think it's Friller in the Discord, was asking if we want to do a complete like walkthrough of chapter 7 in Axler. I said, well, certainly. I'm happy to do that. Even after like chapter 8 and 9, we can do that too, if that's something that we want. Okay, I'm certainly happy to do so. But anyway, in which case we will go through the SVD more carefully. But today we'll just assume that, which is something we often do when we read math. You can't just prove every necessary result, and this way you get bogged down. Anyway, the definition of singular values is actually quite straightforward. The singular values of t are the non-negative square roots of the eigenvalues of t star t. So given a operator t, a linear transformation t, let's look at t star t. We know this is positive operator. Right? This is a positive, we just showed that. It's a positive operator, therefore its eigenvalues are all non-negatives, which means the non-negative square roots exist. So these are the singular values, listed in decreasing order, each included as many times as the dimension of the corresponding eigenspace. So basically, we are counting multiplicities. So the eigenspace of t star t is the time that a singular value would appear in the list. Okay, so that's the singular value, definition of singular value. Okay, well, let's put that down because we need that in the proof of polar decomposition. This is the SVD for operator. In regular linear algebra, for example, the one I've shown in the U Waterloo's Open Math website, SVD is only introduced in the form of matrices. But it's actually not that much of a generalization. Okay, don't get scared away by this operator formalism. So 7.65, definition of singular values. Okay, suppose we have t in L of VW. The singular values of t are the non-negative square roots of the eigenvalues of t star t. Okay, listed in decreasing order, each included as many times. Why is this correction non-negative? Okay, okay, that's weird. As many times as the dimension of the corresponding eigenspace. This is so-called geometric multiplicity. The dimension of the corresponding eigenspace is called the geometric multiplicity of the eigenvector, of the eigenvalue. So dimension of the corresponding eigenspace of t star t. Definition of singular value. Okay, so now we have the singular values Let's put the result next to it. SVD. Singular value decomposition. Here, SVD. SVD for T in LV to W. Suppose T is in LVW and the positive singular values of positive singular values of T are S1 to Sm. And this is with multiplicity considered in the definition of singular values. Then there exist orthonormal lists. Notice it doesn't say basis, it just say orthonormal list. Orthonormal list E1 to EM in V and F1 to Fm also M. Okay, so the two lists are of the same length in W, such that TV can be written in this form for every V in big V. Okay, so that's the SVD for operator. Right, that's the SVD for operator, and we can compare this with the more familiar, hopefully, version of the SVD for matrices later. Okay, let's first put this down. The statement for SVD for operators. Let's go. This is 7 point. We'll assume this result and use it to prove polar decomposition. Singular value decomposition. SVD. Okay? Suppose T is in LVW and the positive singular values of T are S1 all the way to Sm. The positive, okay, this is positive. Singular values can be 0, right? Because singular values are only non-negative square roots. It can be 0. Here we're only using positive singular values. So S1 all the way to Sm are the list of positive singular values with multiplicity considered, counting multiplicity, geometric multiplicity in fact. Positive singular values of T are S1 to Sm. Then there exists orthonormal bases, or sorry, not bases, lists E1, or E1 all the way to EM in big V, and F1, or F1 all the way to Fm in big W, such that you have this equation. So TV equals S1 singular value times V and E1 taking inner product okay, and then F1. And then the other terms all have the similar structure. You add all the way to Sm inner product with inner product of V and Em times Fm. Okay. All right. So this is the SVD for operators. It's not an operator. This is SVD just for linear maps. An operator is in LV. Okay. This is just a linear map, not an operator. Not necessarily an operator for every little v in big V. Okay, cool. That's the SVD. Okay. Compare this with the more familiar SVD for matrices. Here. SVD for matrices. So we have um, a rectangular matrix A. A is P by N with rank greater or equal to 1. Then there exists P by M matrix B with orthogonal columns. P by M orthogonal. Okay, that's this may also be a rectangular matrix. Right, so that's a rectangular matrix P by M with orthonormal columns. So B is not necessarily an orthogonal matrix because orthogonal matrix is a square matrix. Here we're only saying that the columns of B are orthogonal. And M by M diagonal matrix D, M by M diagonal matrix D. So this is a square matrix in the middle and a positive numbers on the diagonal. I'm pretty sure the positive numbers are the singular values, are the non-zero singular values. Okay, singular values are all non-negative, and D consists of the diagonals of D. The diagonal elements of D are the non-zero singular values of A. And finally, M by N. M by M. Does that make sense? Are you sure, Axler? Is it not M by N? Hang on, let's draw a little picture. I have paint. Are we sure about that? Because this smells a little bit weird, huh? So A is P by N. Okay, so this is P, this is N. All right, this is A. This is supposed to be B times D times C star. Ah, okay, C star. C star is M by N. That's correct. So P looks like this. B looks like this. B is P by M. D is a square matrix in the middle, M by M, and C star is M by N. Okay, this is C star. C star is M by N, therefore C is M by M. Okay, so nothing wrong with that. Okay, so the size makes sense. This is a usual, I mean, this is not that usual because the usual version of SVD looks like would look like this. So the usual SVD would have the following form. If you go to Wikipedia, I mean, actually, let me do that. Singular value decomposition. It's a little bit different from Axler's statement here. Yeah, this is the usual SVD. You see, here you have a matrix M. That's rectangular. We write M as U times big sigma times V star, where U is M by M unitary matrix, so that's a square matrix, and V star is also M by N, is also square, unitary matrix, and in the middle, big sigma has the same size as M. So why does Axler's version looks a little bit different from this one? Well, it's because in Axler's version, all the zero singular values are suppressed. That's why. Right? That's why. So you don't write the zero entries in big sigma. Okay, and for that you would have to remove all the columns in U and rows in V star, that corresponds to 0 singular values. So this way, in Axler's version, u and v star are rectangulars as well. Okay, so I mean, nothing is really lost here, because you can always recover this form, the Wikipedia form, from Axler's form by doing what? Well, you can, for example, here B has m columns, right? You have B have m columns. If you want to extend B into a square matrix, you can just use Gram-Schmidt. You can just use Gram-Schmidt so that the square matrix that arguments B would have the same identical m columns, and the rest of the additional columns together with the first m columns forms an orthonormal basis. You can always extend a linearly independent list, okay? And here you can extend an orthonormal list. That's totally doable. So this way, B becomes a square matrix, just like in the Wikipedia form. Okay, so enough said. But here, what we're really using is the operator form. Right? What we're really using is operator form, and we're going to stick to that. So we already put that down in our notes. We're not going to go through this proof because that's not our main goal. Let's go to the spectral, not spectral, but what's that? The polar decomposition. Here, polar decomposition. There's so many interesting results in Axler's book, huh? Anyway, so this is SVD. Yeah, this first sentence is SVD. Okay, and then we extend. You see, this is exactly what I just said. You extend those two lists. Extend E1 to EM, so that it becomes E1 to EM, and that's an orthonormal basis. E1 to EM is an orthonormal list. E1 to En is an orthonormal basis. So this way, it's like in the matrix form, you end up getting two orthogonal matrices or unitary matrices as the sandwich bread. Okay, right? That sandwich is a diagonal matrix. Okay, so that's what it does. I mean, we don't even need the details of how you extend that. It's guaranteed to exist by Gram-Schmidt. So just say extend. That's totally okay. Okay. So how is everyone following the discussion? Okay, is this still? I know SPD is arguably one of the hardest topics in linear algebra 2. So I just walked through the statement. I didn't prove it. Hopefully that's okay. All right. We're focusing on the main goal here. Okay. If anybody has any question, which yesterday I forgot to read messages. Anyway, if you have any question, just say in chat. Okay. Or if you want something that I need to go over, I'll happily do that as well. Define S. Okay, so now here comes the real existence proof, right? We want to exhibit such a unitary operator. S. Define S to be this. It looks like we're just removing the singular values, huh? Interesting. So, and by the way, what does this do? What does V inner product with E1 times F1 do? What does this do, huh? This looks like a rather arbitrary operation, but what does this really do? Well, the intuition is as follows. So let's say this is E1, E2, and E3. And here's an arbitrary vector V. VE1 is the orthogonal projection of V on E. Okay, so this is rather terrible drawing. Okay, so imagine this is the direction of E1. u1 is a unit vector, and this is v. Okay. The scalar projection of v onto the direction of e1 is this dot product or inner product v and e1. You can easily check that. So we're taking the scalar projection of v on the direction of v1 and use that scalar projection to scale f1. Remember, f1 is a different set of bases in the same space. So, okay, this is f1, f2, f3, still orthonormal. So we're taking this scalar projection and use that to scale f1. And not just that, we're going to scale it one more time using the singular value. So that's what the first term does. And here in S, we're essentially doing the same procedure, but without multiplying the final singular value. We're still taking the scalar projection v onto the direction of e1 and use that scalar projection to scale f1. And you do the same for all the basis vectors f1 to fn. Okay? So that's what it does. And then I guess it's just a straightforward computation. You check this indeed satisfies the definition of unitary operator, right? You just need to check it preserves length. And here, because all the f1s all the way to fn are also normal, the squared length, you can just use Pythagorean theorem. Pythagorean theorem here, Pythagorean theorem here, you get v squared. Okay? Because all the cross term vanishes, right? Because f1 all the way to f1 all the way to fn are mutually orthogonal. Right? So, by the way, and this step right here, is exactly the same as saying the distance square r squared equals x squared plus y squared plus z squared. Imagine you have a vector in 3 space, coordinates x, y, and z. What's x, y, and z? X, y, and z are the components of the vector onto each axis, right? So that's exactly the same as taking inner product on each axis. Taking inner product with the unit vector along each axis. So this is the length squared equals the component squared, taking the sum. All right, so this is straightforward. Even though finding out this proof is not easy, right? It's not easy because how did we in last week's stream figure out how do we construct such a decomposition? Well, this is what I did last week. I took the SVD2. I tried a few approaches and then settled down to SVD and say, okay, I'm going to write F as U times sigma times V transpose. Because here is real matrix, so we don't need the star, we just need to transpose. Okay, so, and based on that, I'm going to cook up the the positive definite matrix as well as the orthogonal matrix. So I did a trick here. How did I do that? Well, I did a trick on I inserted U transpose U. This way gives us a decomposition. So if I put a U transpose U between sigma and V transpose, the first component is the first circle is a positive definite matrix. In fact, this should be the square root. And the second part, U times V transpose, is another orthogonal matrix. So that's F equals S times U. And similarly, you can put the combination of V transpose V, that's an identity matrix between U and big sigma. And the first circle is orthogonal and the second circle is positive. So there's that. What I struggled last time is not the existence part. I used SVD to show the existence part, but I struggled with the uniqueness part. I struggled with it. I couldn't quite nail that. So here in Axler's proof, we're also using SVD. We're also using SVD to construct S. Right? We're using SVD to construct S. That's exactly what's did here. And we need to verify that whatever is being left over is the square root. Right? So we have S. S is unitary, but we still have to show that S times the square root of T star T equals T. Right? So let's do that. Apply T star to both sides of 9.94. Sorry, 7.94. What's that? Okay, here we're applying T star to both sides. Okay, T star here. Where should we put T star? Well, this is a scalar, so T star goes next to F1 all the way to T star all the way next to Fm. Right? What do we have? S1 square. Then using the formula for T star given by 7.77. Okay. Yeah, that's the property of T star. That's the property of T star. So essentially, in SVD, the two lists E1 to EM and F1 to Fm are not arbitrary. So they have this nice property. Basically, if you apply T star to F1, this gives you S1 times E1. That's a property of SVD. Yeah, that's that one I recall. Let's go to 7.77. So, singular value decomposition for adjoint and pseudo inverse. Well, we didn't discuss pseudo inverse in this discussion at all, but let's just take a look at T star. So what happened? This is TV. We just showed. I mean, we just went through the statement. But what happened if you apply T star? And by the way, what does T star? What's the domain and codomain of T star? T star maps from W to V. No. T star should map from W to V. Let's take a look at the definition of T star. The definition of adjoint. Very early. It's like the transpose, right? See, T star is from W to V. Here, TV is in W. Little tv is in W. Little w is in big W. So the inner product here refers to the inner product in the space W. And on the right-hand side, we're talking about the inner product between V and T star W. Here on the right-hand side, it is clear from context that the inner product on the right-hand side is the inner product in V, the inner product in the domain. So T star W must refer to a vector in big V. So T star acts on vectors in W and gets back to V. Right? So because think about the size arrangement of a matrix and its transpose. So this is entirely natural. So what we're doing here is we take an arbitrary vector, little w, yeah, from big W,
T star W behaves this way. T star W is S1 WF1 E1. That's interesting, no? Look at the symmetry between 7.76 and 7.77. Okay, so by definition, hang on. So by definition, F1 squared equal. Yeah, F this is orthonormal. I guess you refer to the square length, philosophlog. Yeah, this is orthonormal, so the square length is indeed 1. Okay, hopefully we're clear about that. Yeah, so that's the action of T star. If we specialize, so to say, if we specialize W to be let's say Fi, what happens? Well, then you would have Fi with F1 in a product. No worries. I mean, we'll be back in 30 minutes to make breakfast short. Sure. Yeah, and here you have F1 with Fm in a product. Fi. The only term that would survive would be the Fi term. Because Fi is F1 all the way to Fm or orthonormal. The only term that survives in I'm busy is my alternate. Okay, cool. Okay, so F1 Fi all the way to Fm Fi, taking inner product, all these inner product only has one non-zero term. That's Fi with itself, which is just 1. Okay, this is just 1, and you would have a scalar S1, SSI at the front and EI at the end. So every other term gets killed, so you just end up getting with T star Fi equals SI EI. And what's nice about this is that the previous equation tells us T of EI equals SI of Fi. And the reason is the same. Substitute V equals to EI. On the right hand side, only one term survives. The inner product of EI and EI itself, which is 1. So SI and Fi remains. So these two lists are not arbitrary. They have a nice correspondence. If you apply T to one of the E's, it gives you the corresponding F. And if you apply T star to one of the F's, it gives you the corresponding E. And the scalar factor is the same, the singular value. Okay, so actually I haven't used singular value for a long time, but I vaguely remember this relationship. So that's it. So that's the reason why we have we apply the T star on both sides in the SPD. It gives us that nice equation. You know what? Let's put this result down. Right? This is just extension for the previous SVD, right? The previous SVD is only about TV. Here, let's put T star V here as well. Let's put T star V as well. Okay. Yeah, this is 7.70. So it looks like 7.76 is the same as we just wrote here, right? So let's just put that as 7.75. 7.75, okay. Let's put an equation number 7.76 here. And then, oh, it says it's supposed that. It's supposed this is true. Well, we already know this is true, no? Why do we need to suppose? We know there exists
Actually, why are we supposing that? Because okay, it doesn't matter. Um, and let's just keep writing. And you have T star W equals S1. Change everything here. Just change the letter. You swap E and F. That's the T star operator. Okay, so that's the T star operator. And go back to 7.75, section 7.5. Okay. Yeah, here. So this makes sense now, right? If we apply T star to F1, it gives us S1 times E1. So the first term becomes S1 squared, inner product, and then E1, like so, like so. And what do we know about um, the uh, the square root operator? What do we know about the square root operator? Well, the square root operator, as we defined yesterday, um, R here, right? The square root operator we defined yesterday works this way. It works this way. So um, yeah, suppose you have E1 to En that are eigenvectors of T, with eigenvalues lambda 1 to lambda n respectively. Then the square root of T, the square root of R of T works this way. R acting on EK is the square root of lambda k EK. And here, because we're taking the square root of T star T, this the matrix or the operator T star T has eigenvalues S1 squared to Sm squared. Remember, singular values are defined as the non-negative square roots of the eigenvalues of T star T. So these are eigenvalues of T star T. So the square root of T star T acting on V um, gives us S1, blah, 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 and Sm. So that comes from yesterday's definition of square root. Okay, so now we're just checking S times the square root of T star V, T star TV equals blah, 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 TB. Right, so this simplifies to TB. And this finishes the proof. Exercise 27 shows that the unitary operator S produced in the proof is as close as a unitary operator can be to T. Well, that's super interesting. So we're talking about an approximation, huh? This is mind-blowing, actually. This exercise is mind-blowing. So that means the polar decomposition can be defined in an equivalent way. S is as an optimization problem. Wow. Yeah. So yeah, you can define polar decomposition in an alternative way. Wow, that's super interesting. But anyway, let's just skip that for a moment. Perhaps that's useful in applications, huh? Because sometimes I don't know what time, but you might want to approximate a matrix by an orthogonal matrix. Let's say you have like an arbitrary linear operation like this. You say, okay, what's the closest rotation to this? Well, you do the polar decomposition. I wonder if that ever has an application. But anyway, it doesn't matter. So, so what's the? How can we get a uniqueness proof from that? Or if we go back to actually, I'm not super excited to write this proof pretty much verbatim because this seems already pretty clear. We already justified everything along the way, right? So I mean, we can't do the writing after. I mean, I'll do the writing after the stream to make the notes self-contained. But I'm still thinking about like Vizzy's problem, right? So what's what's the structure of the problem? So the structure of the problem is as follows. Part one is an eigen decomposition problem for a specific matrix with numbers. So this is very mechanical. So part one is relatively easy, okay? And part two is to part two here is to show the existence and uniqueness of the positive square root. Right? So show the existence of uniqueness of positive square root, which we use the spectral theorem to show existence, but we didn't show uniqueness. Good. Okay, so that's the thing we need to fill up. I guess this is very similar to the uniqueness proof we did yesterday. That's the part two, but the key here is part three. I mean, the real question is part three. It feels to me, okay, this question has this structure that you're supposed to use the previous part to do the next part. You know what I'm saying. So let's just say we're not using SVD, even though it works. Okay, it works to show existence. Can we use can we just use the existence of the square root that's showed in part two? We showed that in part two. Can we just use the existence of the positive square root to do part three? That's the natural approach, right? So that's the I think that the question is meant to be that way, because without any hint whatsoever, and the question calls for SVD, that's not natural based on just the arrangement of the question. So I'm thinking, can we just use a different approach? Okay, that's the idea. So here, f is non-singular. This is our idea. Okay, let's take the u. Let's take the unitary operator, not the unitary operator. Let's take t. Let's take t to be the square root of v transpose, f transpose f. Can we do that? Let's take t to be the square root of f transpose f. Well, the square root of S transpose F has to be a positive definite matrix, symmetric positive definite matrix. So how we're going to construct V this way? We already, in part 2, we already showed that T exists. Square root of F transpose F exists. This is well defined and is unique, even though we haven't written the uniqueness proof yet. Let's just say this is T is well defined. How do we get V? So I'm ditching the SVD approach. Okay, I'm trying to connect part 2 and part 3. How do I get V? I'm not quite sure. Because in Axler's proof, to get this orthogonal matrix, we make use of singular values. Can we get that straight from the square root? Already have the square root, let's say. Let's revisit Axler's proof. So the square root acting on, yeah, the square root. Okay, so let's suppose you have eigenvectors, right? Eigenvectors of t star t, which are e1 to em. These are eigenvectors. Right, these are eigenvectors. Cool. You first do an eigen decomposition of an arbitrary vector v, right, and then you're expanding, right? We're expanding the t star tv into the eigenbasis. Taking the square root gives us this. Can we engineer S from here? Can we engineer S from here? What is S? Well, S as is written here looks like this. But we still need the F, right? Still need the F. And by the way, F should be, yeah, F should be the eigenvectors of t star. E1 all the way to EM, E1 all the way to EM are the eigenvalues of t star t. And F1 to Fm should be the eigenvectors of t star. This is something I recall from my knowledge base, but not, we haven't seen that in the book. I'm pretty sure there is. So F should be the eigenvectors of t star. You can just take my word for that. So how do we, my goodness. I mean, even though we understand this proof, this is still not making progress about this problem, huh? Like the challenge right now is to connect part 2 and part 3. I'm assuming we can write down the square root of F transpose F. Let's say that's the square root of F transpose F. Let's call that T. So F equals Vt. That's the F equals Vt. That's the polar decomposition. Okay, so if we assume F equals Vt, where V is orthogonal, T is symmetric positive definite, then what happens? Well, we can write F transpose F, which is T transpose V transpose Vt, which is T transpose T. if we assume f equals su, if we assume f equals fu, then f transpose is what? Is su u transpose s. S transpose is s transpose. So I guess the candidate for s would be the square root of f transpose. Just the educated guess. And then how do you get v and u? Okay. My brain is freezing right now, so let's ask AI. Let's ask AI. You'll hear, let's say, um, let's just set up the problem the way the question is aimed for. So we have the existence of the positive square root. So we wish to show polar decomposition. Right? That's the overarching idea. Okay, so assume we know, assume the fact, okay, that for every real symmetric positive definite matrix, there exists a unique real symmetric positive definite. So here it uses positive definite matrices, so that means the eigenvalues are all positive. Okay. In Axler, we just say positive operator, which includes matrices with 0 eigenvalues. That is its positive, the symmetric matrix C. That is its square root. Assume this fact. We wish to show polar decomposition as follows. So let F be a square matrix non-singular. Decomposition. How do you spell? Okay. Let F be a real square matrix. F. Of course, AI can make mistake, but we're going to apply the same auditing procedure that we read normally, so it's not going to be a big deal. So be non-singular. F equals, let's just show F equals Vt, okay? F equals Vt for some real symmetric positive definite matrix T, and for some, let's just say existence, okay? Let's not worry about uniqueness yet. And for some orthogonal matrix V. Okay, only existence, only show existence. for now. Assuming this fact, how can we show polar decomposition? We want to prove the existence of polar decomposition. Yeah? Construct a positive definite matrix. Yes, C equals F transpose F. Okay, C is symmetric for sure. For every non-zero vector X, we have, yeah, this is correct. So C is positive definite. Yeah. So C is positive definite. We can take the square root. So T is the square root of C. T is the square root of C. Yeah. How do we define V? What? Oh, okay. I was freaking stupid. So V is just, we just want, we, my goodness. So T is invertible. So V is just FT inverse. Okay, so V is just FT inverse. And we need to show V is orthogonal. Well, you just verify that. V transpose V is identity, huh? We just want to show that. So V is FT inverse. So V transpose V, V transpose V, you simplify that, you get what? And T is symmetric. Well, this notation is nonsense, no? You don't have, what's T to the minus T? I guess it's the inverse taking transpose. Yeah, the inverse taking transpose is still the inverse. Okay, so, and F transpose F is T. F transpose F is T, so one of the T cancels. Yeah, no, just T square cancels entirely, gives you I, so V is orthogonal. Then you have the left polar decomposition. My goodness, this, okay. I completely stuck at this place. Okay, that's kind of humiliating. Well, this is existence. How do we prove uniqueness then? So ChatGPT simply take the V equals, because I was so stuck with Axler's idea of how do you, let's say you use S as a, in the form of singular value decomposition. Okay, so here we have a very short solution. You just take F times T inverse, such as life. I know. Right, Maxter. Yeah, you're right. This is humiliating. Okay. Anyway, so how do we prove uniqueness? Is the polar decomposition? How do we prove uniqueness? Uniqueness of polar decomposition. Okay, so you have, this was the setup I had last time. So now we do what? We calculate F transpose F. This, once again, it comes back to F transpose F again. Is it intuitive to pull out the inverse of T? I suppose so. I mean, it should be rather intuitive, right? Because what the ChatGPT did was, let's suppose you already defined T and you want F equals Vt. Then you simply define V to be Ft inverse. It's like divided by T on both sides. And then separately verify that V is indeed orthogonal. right? It should be rather intuitive, right? It's certainly more intuitive than SVD. You know what? I was kind of proud of myself for pulling out this trick last time, right? I inserted this identity in between to construct these two. I wouldn't call that intuitive. It's just something that clicked in my mind, and I come up with that construction, right? But I think this should be the natural solution to the problem, right? We do the uniqueness of the square root. We do the uniqueness of the square root in part 2, and then so you can define t in part 3, and then v is simply ft inverse. Boom. Right, okay. Anyway, so let's keep reading here. So how do we prove the uniqueness? We need to show v1 equals v2 and t1 equals t2. Compare f transpose f. What do you mean by compare? Well, I guess compare f transpose f in these two forms, right? You have f in terms of v1, f equals v1 t1 and v2 t2, right? So, well, you got f transpose f. Here we're only using v1 t1, and because v1 is orthogonal, this becomes t1 squared. And do bear in mind that t is symmetric positive definite, so you don't need t1 transpose. You just need t1. This is t1 squared. So f transpose f is t1 squared. And then you do the same. You got f transpose f is t2 squared. And because the square root is unique, because we didn't quite manage to show uniqueness of the square root last time, so that's why we just couldn't think about it, right? We couldn't think about using it, right? So because t1 and t2 are both positive square root, and the positive square root is unique, so therefore t1 and t2 are the same. So if t1 and t2 are the same, well, because v is what? v1 is ft1 inverse, v2 is ft2 inverse. So if t1 and t2 are the same, v1 and v2 are the same. So that's done. Wow. Humiliating. What can I say? My goodness, I was stupid. All right. Perhaps we can revisit the proof of uniqueness of square root, huh? Right. So here I use the spectral theorem, right, to construct the positive square roots. And it actually took us a bit while to prove uniqueness. Well, I mean, in Axler's book, right here. I wonder how ChatGPT would handle that. Okay, so that's good. So let's take a step back. Take a step back. Let's look at. Take a step back. Let's now look at the existence and uniqueness of positive square root. Okay. Of positive square root. We know that the existence can be shown using a spectral theorem. Spectral theorem, or decomposition, spectral decomposition, how to prove uniqueness. Suppose, all right, yeah, that's exactly how we constructed the square root last time. The interesting part is uniqueness. Indeed, it is interesting. It says prove using simultaneous diagonalization. What does that mean? Suppose D is symmetric positive definite matrix satisfying D squared equals C. Since D is symmetric, spectral theorem gives this decomposition for sure. Here the mu's are the eigenvalues of D. Okay, now take the... Okay, D is the square root, no? Yeah, D is the square root. So D squared equals C. What? Hang on. What does uniqueness mean here? What does uniqueness mean here? Uniqueness says there exists a unique symmetric positive definite matrix D satisfying D squared equals C. I guess simultaneous diagonalization refers to that the columns of this Q matrix diagonalizes D and C simultaneously, right? That's got to be the meaning. So you have this diagonalization for D. Yeah, no problem because D is symmetric. And D is positive. You just calculate D squared. That gives you C. That gives you C. So, wow. It doesn't say C can be any other form, huh? Thus, the eigenvalues of C are precisely mu I squared. Hence, D is exactly the square root constructed in the existence proof. What the hell? Existence is immediate from spectral theorem. Yeah, that's true. I don't buy this simultaneous diagonalization part. It does not look like a uniqueness proof to me. Right? It just say that this form this part is just say this form of Q times diagonal matrix of square root of lambda 1 all the way to square root of lambda n times Q transpose. This is a square root. Nobody's questioning that. But why is this the unique square root, huh? Right here it just said, here it says, okay, if D looks like this, but why simultaneous diagonalization? That's not assumed, no? Because even if you just start from, okay, you have a D that is symmetric, right? Why is it that a priori the same D has to be using the same columns as Q? I mean, simultaneous diagonalization is not a priori given. So here, what this proof does is that if we're assuming C and D are simultaneously diagonalizable, then D has to be in this form. I mean, which is trivial. Right? So I don't buy this part. Feels hand wavy. Exactly. So let's look at a shorter and more conceptual. Okay. Here, this is more standard. Suppose D1 and D2 are symmetric positive definite, and you have this condition, right? That's where we started from, and I got stuck last time. The evidence is still here, right? I wanted to show D1 equals D2. Okay. Okay, this is, yeah, that's right. And then what we do, we're going to multiply d2 on both sides as it seems. Is that what we're doing? Since d1 equals d2, we have d1 times d1 d2. Hang on, what is this doing? Equals d1 d2 together d2. Why is that? Why is that? d1 equals d2. Yeah, we have, so d1 is c. This says c d2 equals d1c. What? What the hell? Lagrange interpolation? What the? Okay. Okay, this feels okay. Redo the uniqueness part. Okay. Start from d1 squared equals d2 squared equals c. Show d1 equals d2. Diagonalize c, sure. Transpose d1 and d2 in this basis. Transport into this basis. Okay, you can do that. You can certainly do that, but we're not claiming that E1 and E2 are diagonal. Okay, we're simply defining E1 and E2 to be these two matrices. Feels unnatural, but whatever. It just, I mean, E1 and E2 are well defined, sure. You can calculate E1 squared. Yeah, E1 squared is indeed Q transpose D1 squared Q. And D1 squared is C, and that's lambda. So E1 squared is lambda, and similarly E2 squared is lambda. Therefore, it suffices to show that if E is symmetric positive definite and E squared is lambda, or lambda is diagonal with positive entries, then E is, yeah, okay. So that E must be diagonal. That E must be diagonal. So how on earth would you think about that? Well, my goodness. So you take E times lambda, which turns out to be lambda E, right? So that's just the multiplication becomes, okay, we'll verify that, but let's just take that for a second. This should be just matrix multiplication. Therefore, whenever lambda I not equal to lambda j, we must have eij equals 0. Whenever, all right, what's lambda I and lambda j? That's the ij entry. Ij entry. Okay. Now consider one block corresponding to a repeated eigenvalue. Okay, a repeated eigenvalue means you have I not equal j, but lambda I equal lambda j, which means there's a repeated eigenvalue. Does that also mean eij must equal to 0 then? What the hell? Hmm. You know what? This is one of the rare problems that the uniqueness is much harder than the existence. I've got to put it that way. So here, how do we, like, what's the overarching idea that gives us d1 equals d2? So we show e1 equals e2, right? And we show e1, how do you show e1 equals e2? Well, you just say if e squared is lambda, then e has to be this way. So that boils down. That boils down to the proof. So, which I think is more natural, I guess. The idea is lambda is a diagonal matrix with positive diagonal elements, and you have a matrix E, which is SPD. Okay, and you have a matrix E that's SPD. If E squared is lambda, then E is uniquely determined as such. Right? So we're trying to prove that. Okay, so here, if the eigenvalues are not the same, right, eigenvalues lambda I not equal to lambda j, then eij must equal 0. But if we were looking at repeated eigenvalue, so E is a block diagonal corresponding to distinct eigenvalues of C. Yeah, that makes sense. Now consider one block corresponding to the repeated eigenvalue lambda. On that block, right, on that block, because it shares the same eigenvalue, so E squared is lambda I. Since E is symmetric, you use the spectral theorem. Okay, here you're using a different basis, potentially different basis, P. That's okay. Hang on. This is wrong, huh? Where did P go? Where did P go? I mean, I'm not saying it's wrong, but I'm missing something here. E is symmetric, then diagonalizing E gives us this form. Squaring that, we get mu squared equals lambda. What do you guys think? This still feels a little bit awkward, huh? I don't. Hey, sorry to hear about your main channel. Hope it's restored. What's the problem you're working on? It's this problem. It's this problem right here. I'll walk you through. So this big problem has three parts. The first part is a linear algebra problem. The first part is strictly computational. You're given a 3 by 3 matrix with numbers. And it turns out to be a symmetric matrix. So you're asked to find the eigenvalues and eigenvectors, which, unsurprisingly, you would have real eigenvalues. And the eigenvectors are all orthogonal. Right? And we can, based on the eigen decomposition, easily calculate the positive square root. And this is a procedure, because if you have a matrix that's orthogonally diagonalizable with non-negative eigenvalues, you just take the square roots of the diagonal matrix and leave the two orthogonal matrix on the left and right the same. This way it gives you
the square root. And this can be easily generalized to arbitrary positive symmetric definite matrix. The problem is to show the square root is unique. That's the problem. Sir EJ. Okay, that's the problem. And we struggled big time. I mean, I struggled big time. Last week, I couldn't show it. And so I set up the problem. I set up the proof. I suppose there's d1, d2 such that d1 squared equals d2 squared equals c. And I want to show d1 equals d2. I couldn't nail it. Okay? And so for that, I consulted Axler, linear algebra done right. And here's the proof in that book, which we rephrased, sort of. But definitely we understood that proof for sure. So Axler's idea was to use a property of linear map. It basically says if a linear operator, if the image of a linear operator on a given basis is fixed, then itself must be unique. But it feels there should be a more natural proof, like the setup here, which I asked ChatGPT to do, but I'm still unconvinced. I'm still unconvinced about the proof. So there's that. I mean, I'm still confused about this part. So basically what ChatGPT does is that it first diagonalizes C, which gives us the Q matrix. The matrix of, or the matrix whose columns are orthogonal basis of Rn, right? And here we have d1 and d2, supposedly two positive square roots, and we define e1 and e2 to be this way. So we're trying to show that e1 and e2, those two e's are also diagonal. So basically we're trying to show the Q matrix diagonalizes d1 and d2 too. And here's the AI's steps. Okay, so we have e1 and e2, and we want to show that e1, e squared is lambda. We want to show e squared is lambda. I'm sorry. If e squared is lambda, right? If e is if e satisfies e squared equals lambda, then e must look like diagonal square root of lambda 1 all the way to square root of lambda n. So essentially E is determined. If E is unique, then well, D1 and D2 are the same. Okay, so we want to show that E must be diagonal. Remember, E is defined this way. The two E's are defined this way. First, we make a calculation, and it turns out that E and lambda commute. Lambda is the diagonal matrix whose diagonals are the eigenvalues of C. Right, so this is a straightforward verification. E and lambda commute. In entry form, it looks this way. Okay, we'll verify that, but this looks correct to me. But here's the thing. If lambda I and lambda j are not the same, we have Eij equals 0. So the off-diagonal term is for the distinct eigenvalues. Okay, let's draw a picture. So what does this say? Lambda I minus lambda j times Eij equals 0. So imagine this is the E matrix, all right? You got the diagonals You got diagonals here. It says if lambda I and lambda j are not the same, then Eij must be 0. And Eij must be 0. So that's what it says. But the situation for the repeated eigenvalues is something I have not yet understand. So let's say you have these two diagonals. So this is lambda here, this is lambda here. How do we show this entry is 0? Can we do that? What does AI say? E squared equals lambda I. Yeah, this block right here, if you square that, it gives you lambda. It gives you, well, it gives you lambda times I. Since E is symmetric, the spectral theorem gives E is symmetric. Okay, the spectral theorem gives the diagonalization as follows. Mu square I equals I still don't buy E is the square root of lambda times I. E is P diagonal. Okay, I see. I see. I see. So that block equals square root of lambda I. That block. So if we're just considering that block, that means all the mu's are the same. So it just becomes square root of lambda I times I. And P transpose is I. So indeed E is the square root of lambda I. Yeah, this is right. This is now, yeah, this is an actual proof. Yeah, I give it to that. Because basically, if you have repeated eigenvalue, right, then the part with repeated eigenvalue would have the same would have the same mu's. The mu would just be square root of lambda. So this part of the diagonal matrix becomes the square root of lambda times I. P times the square root of lambda times I times P transpose would just be the square root of lambda times P transpose. And P transpose is identity. So it reduces to E equals to square root of lambda times identity. Yeah. Yeah, so that's actually a valid proof. Yeah, so that's actually a valid proof. So anybody following? Let's write that down. Let's write that down. So this is actually a different proof from Axler. We'll take our what we learned from Axler as one valid solution. But here AI give another solution. So let's write that down. Okay. Delete that. The uniqueness of square root. Sorry, let me make some space here. Okay. Oh no. Okay, let me just put it at the end, I guess. Put it at the end. Oh, I'll delete this part. Not delete, but remove this part to the end. We'll do part 3 later. Okay, question.
if B squared equals A is symmetric, then B shares the orthonormal basis with A. Hang on. Let me read your comment. If B squared equals A and A is symmetric, then B shares orthonormal. Yeah, that's what the solution is trying to show. Right. So shares orthonormal. That's what the solution is trying to show. Eigenvalues plus or minus square root, and since B is yeah, it's the part that it shares the orthonormal basis that needs to be shown. Right. So that's the idea. So let me rewrite this. So suppose d1 and d2 are real, symmetric, positive, definite, such that d1 squared equals d2 squared equals c. Okay, so let's do the spectral theorem. By spectral theorem, C equals Q lambda Q transpose. Okay, and then we define E1 to be a Q transpose, yes, Q transpose D1 and Q. Sir EJ, you said then B shares orthonormal basis with A, which is exactly what we want to show. Right, so the idea is the same orthonormal basis or the same orthogonal matrix that diagonalizes C also diagonalizes D. Right, so we need to, that is to say, we need to show E is diagonal. Right. Okay. E2 is what? Is Q transpose D2 Q. That's you get these E1 and E2, right? E1 and E2. So it suffices to show E1 and E2 are the same. Right? To show D1 and D2 are the same, suffices to show E1 and E2 are the same. Because E1 and E2, from E1 and E2, you can easily write D1 and D2. D1 is Q E1 Q transpose. And D2 is Q E2 Q transpose. Right? So suffices to show E1 equals E2. And also it is clear that E1 and E2 are both symmetric. Okay. E1 transpose, just quickly calculate that. E1 transpose is Q transpose D1 transpose. But D1 transpose and then Q. But the thing is, the Q transpose which is exactly as Q transpose D1 Q, and that's just E1. Okay, so E1 and E2 are symmetric, which means you can apply spectral theorem to E1 and E2. You can apply spectral theorem to E1, E2. It's just write EI, okay, EI. And this will read EI equals P diagonal mu1 all the way to mu n P transpose. Okay, let's just remove the subscript for E, because we just need to analyze for one such E matrix where is E1 or E2. Okay. Okay, so E commutes with lambda. Observe that E lambda equals lambda E. Okay, let's show that real quick. E lambda equals lambda E. So what's lambda? Remember, D1 and D2 are the square roots of C, right? If you could use that. The lambda square, no, not lambda square, but how do we, what's that? E, lambda square is E square. Yeah, E square is lambda square. First, let's observe E square is lambda square. We need that first. Question, okay, makes sense. E square is E square, let's say this is Q transpose D Q Q transpose DQ. That gives you Q transpose D square Q, and D square is C Q, which is lambda. Yeah. And then E lambda equals lambda E becomes trivial. It's just E cubed. Right. Okay. So there's that. But what does this say in component form? What does this say in component form? Let's use row times column, I suppose. Imagine this is E. This is lambda 1. Let's say this is lambda lambda I, lambda n, this way. Okay, the ij's entry, this is the j, okay, lambda j. The ij's entry would be the i's row of ei1, all the way to eij, all the way to ein. Row times column. Okay, and on the right hand side, let's write down the ij's column. Lambda 1, all the way to lambda I, lambda n, the j's column, or I need the j's column. J's column looks like ej1 all the way to eji, and all the way to ejn. Okay, so this is the i's row. This is the j's column, which multiplication gives you the ij's entry, which is exactly just ij times lambda j. On the right, you get lambda I times i's row, j's column, lambda I times eji. But because E is symmetric, eij equals eji. And as a result, eij times lambda I minus lambda j is 0. Okay? So that's the relation. And we're going to do two cases. Here we're running out of space. Okay, let's go to the end. Okay, so yeah, that's a separate question, probability question, which we managed to complete. So here, let's continue here, because now we have two cases. Let me move it down here. All right. Now this should be enough space. So what we have so far? What we have so far? We have d squared equals c. C equals q transpose. No, not q transpose. C equals q lambda q transpose. E is defined as q transpose d q. Right. So this is and these are the setups, and we managed to prove E squared is lambda, and this leads to E lambda equals lambda E, which leads to the coordinate-wise relation, component-wise relation, which says Eij times lambda I minus lambda j is 0. Okay? We show that Eij is 0. is 0 for all I and j such that I and j are not equal, i.e. E is diagonal. E is diagonal, okay? This is our goal here. We wish to show that E is diagonal. So for case 1, which is rather easy, okay, so first let's suppose I not equal j. Suppose I not equal j. Case 1, lambda I not equal lambda j. Then Eij equals 0 is immediate. Okay. So what does this mean? So what does this mean? So E looks like this. Is a block diagonal matrix. So you have so E must look like something like this. So this is the first block where lambda are all the same. Because I don't want to use the subscript anymore, so let's just use lambda superscript 1. So that's the first distinct eigenvalue. The first block. And then you got the second block and so on. Right? Because it says if lambda I not equal to lambda j, so that means if the lambda I comes from lambda I and lambda j comes from different blocks in E. Okay? So E looks like this, which means E's look like this. This is the case 1. Okay? And now we're actually trying to show that, in fact, in each block, you also have a diagonal matrix. Okay, so case 2. Suppose now lambda I and lambda j comes from the same block. What happens if they come from the same block? So that block would look like what? The block above in E is also symmetric. That block is symmetric. That block in E, as we will show, let's suppose lambda I equals lambda j equals lambda, okay? That block in E, as we will show, is the square root of lambda times I. Because the block by polar decomposition no, not polar decomposition. I was doing polar decomposition earlier. By spectral decomposition, reads what? Reads this, right? We did the E is this form. So if you just want the block with the same, you should get E with a diagonal where the mu are the same.
That's what I'm saying, right? That block is reads P diagonal a bunch of mu. And those mu must be positive because um, E comes E is defined as Q transpose DQ, and D is positive, positive definite. Okay, D is positive definite. So reads this, and this is what? And this is exactly just mu P identity matrix P transpose, which is mu identity. And this is supposed to be lambda, and this is and that's the part of E, the block in E. So that's the square root of lambda I. So the block looks like a diagonal as well. So therefore, overall E is overall E is diagonal. So E is diagonal with positive entries, and so this severely restricts the form of E. And E, since E squared equals lambda, E is the diagonal of the square root of lambda 1 all the way to the square root of lambda n. So now E is fixed, the D1, D2 are fixed. Okay? So that's the uniqueness. The uniqueness proof is much harder regardless, right? In whatever method we use is much harder than the existence. The existence is almost trivial, but uniqueness is quite tricky. I guess this is something I don't see very often. Usually existence proof is harder because you need to actually construct the thing, right? Uniqueness is typically easier, but not in this case. Okay, and here, after securing the uniqueness of the square root, well, we just got completely humiliated by ChatGPT. Well, that's actually pretty common, actually. That the after you defined t to be the square root of f transpose f, v is simply f times t inverse. That's it, right? And you just verify this is v is orthogonal. You just verify e is orthogonal, and uniqueness is guaranteed by the uniqueness of the positive square root. Okay, so that's cool. And now, because I'm getting a little bit tired and I have another stream next morning, so let's just quickly think about 2 and 3, see if we can handle that. Can we manipulate these equations and get what we want here? So let's I mean now let's 1 is done, right? Let's see if we can do 2 or 3. So you have f equals su, v equals t, and we just said t squared is f transpose f, s squared is f transpose, and we want t is f inverse sf. That is to say, ft is sf. right? That is to say, ST is FS. Is this true? How do we show FT equals SF? Well, we have these relations. Can we say F squared T squared is F squared FTF? This is F times FT. So I'm multiplying F squared of this equation on both sides. Left multiply F squared on both sides. Is there some shenanigan we can perform? F squared F squared T squared is F squared F transpose F. Okay, let's just leave it that way. And what about, say, S squared F squared? S squared F squared. I'm multiplying F squared to the second equation to the right. You get F transpose F times F. Mhm. Are these two the same? If they're the same, then we're done, right? Actually, no. Actually, no. This is nonsense. This is not what we want. Because I was thinking, oh, this is just ft squared. But no, matrix multiplication is not commutative. You can't just group terms like that. It doesn't work. It does not work. Okay. So that's silly. That's obviously wrong. How do we get to that part? We have T squared equals F transpose F and S squared equals F transpose. Okay, somehow the U and V disappeared. And in fact, they're the same, according to part 3. That's insane. Highly unexpected. But first of all, part 2. Am I also missing something super obvious here? Well, we know that T is the unique square root of F transpose F, right? So how about just verify the right-hand side also satisfy that condition? So let's look at F inverse SF. Let's square that. So F inverse SF, F inverse SF. Okay, F and F inverse cancels. And you get S squared in the middle and then F. S squared by definition is F transpose. So this is F inverse F transpose F. F inverse and F cancel, so this is F transpose F. So therefore F inverse F
sorry, F inverse SF, F inverse SF is a square root of F transpose F. So you see, look at this and this. And all we need to do is to verify F inverse SF is positive. Right? We just need to verify that this is a positive definite matrix. Is this a positive definite matrix? It should be. It should be. So here we show that F inverse SF is a square root of F transpose F, which is nice. And now we need to show this is positive definite. Okay? So let V be a vector. Let's consider the quadratic form for checking positive definiteness, essentially. So let's consider V transpose F inverse SFV. This is a quadratic form. If this is greater or equal to 0, then it's positive semi-definite. Right. If it equals 0, if and only if V equals 0, then it's positive definite. All right, so let's do that. Remember, S is definite. S is positive definite. S is positive. So can we? This is FV. This is not F transpose V. So we showed that this is a square root, but we don't know whether this is positive. Is that the case? I think it should be. Because F is an invertible matrix, so this should be a matrix that is similar to S, right? If it's similar, then the eigenvalues should be the same. If the eigenvalues should be the same. So I'm erasing this. So because this this says that this matrix is similar to S. And S is okay. So let's denote what are other letters out there. R, S, T, U. U is occupied. What comes before R, S? Let's denote R to be F inverse SF. This is the definition of similarity. I mean, there's no need to denote this, but basically, this is the definition of similarity, similar matrices. Since this is similar to F, and similar matrices always have the same eigenvalues, and that's a property of eigenvalues. By definition, you know what? Let's check that, okay? I'm pretty sure that's the definition of similar matrices. Similar matrix. Hang on, there's no similar matrix in Axler's book? Are you kidding me? Okay, let's go to this website, which I highly recommend. It's called UWaterloo. Open Math. I strongly recommend this website. It's got the basics of linear algebra in interactive courses, so it's pretty sure it's linear algebra 1. Inverses and determinants, similar matrices, perhaps diagonalization. Similar matrices, yeah. Yeah, so there's that. Similar matrices. You have definition. Definition. Let A and B be n by n matrices. If there exists invertible matrix such as P inverse AP equals B, then we say A and B are similar. That's exactly the definition. Here F is invertible. So basically, yeah, by definition is similar. Yeah. Your SVD construction surely implies 3. Yeah, you're right. They're the same, no? Yeah, that's a good one. That's a good one because we sort of ditched that, right? We sort of ditched that when we were trying to show uniqueness. I guess it works, right? If you have, I mean, the uniqueness part, right? The uniqueness part of 3. I mean, it's in my opinion. I mean, if you can, yeah, if you use, that's the good. That's the advantage of the SVD. I forgot about this, to be honest. Yeah, Sir EJ, you're totally right. That's the SVD construction. Just gives us the last part for free. All right, awesome. Anyway, so what I'm trying to say is, let's finish this part. By definition, is similar to S, and hence share the same eigenvalues. Share the same values. Okay, I'm writing cursor because the strokes are sometimes broken if I try to use different strokes. Strokes. Okay, I can't speak. It's getting late. Anyway, so hence share the same eigenvalues. And since S is positive definite, SPD, F inverse SF is also SPD. Well, we got to check this is symmetric. I mean, we need to check this is symmetric. Then we can use the uniqueness of the square root to finally nail down that this is the same as T. F inverse SF transpose is what? Is F transpose. S is symmetric, so S in the middle, F inverse transpose. Why this is the same as if you apply a similarity transform to a symmetric matrix, do you still get a symmetric matrix? Right? We're trying to show this is symmetric. Is this a symmetric matrix? I'm not sure. Let's chat GPT it.
Okay. Applying a similarity transform to a symmetric matrix is a result also symmetric. Not in general. Huh. That's where we get a problem. It's not true for arbitrary P. Orthogonal similarity preserves symmetry, but the thing is here F is not orthogonal, not necessarily orthogonal. Here's a counter example, which is pretty cool. So here's the problem here. Why do we have, if this is not necessarily symmetric, I can't use the uniqueness of the square root argument, no? Because I was trying to nail down that F inverse SF satisfies the same condition as T. T is a positive square root. We verify that is a positive square root of F transpose F. It is a square root. We verified that. And it's also positive. It's also positive, but why symmetric? No. Why symmetric? So let's go back to here. Let F have, let invertible F has left polar decomposition. F equals, yeah, so I'm stuck here. I can't show this, I can't even show this is symmetric. Left polar decomposition. Is it left or right? I don't know. What does ChatGPT say earlier? Any polar decomposition necessarily will necessarily have blah 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 uniqueness. Okay. I think it mentioned something earlier about left and right polar decomposition, but I don't know which is which. A complete analysis argument shows that gives the left polar decomposition. So SV is left polar decomposition. Okay, so here we're dealing with SU and right polar decomposition. F equals VT. How to show T equals F inverse SF. All right, let's see. Am I again missing something super obvious here? Okay. Want to show this identity? Yeah, that's no problem. So we want to relate F transpose, FF transpose, and F transpose F.
Okay, yeah, this is just multiply f and f inverse and then regroup. Yeah, okay. This seems highly unnatural, huh? Why is this useful? Because f transpose is s squared. F transpose f is t squared. We now use a fundamental fact. If A is symmetric positive definite and P is invertible, P is invertible. Hang on, where did this fact come from, huh? Hey, A is symmetric positive definite. This follows by the uniqueness of the positive square root is symmetric positive definite and squares to, okay, um, yeah. So you have that and you square root on both sides, I guess. Damn. Wow. Okay, wow, this is highly non-trivial. Or maybe I'm just stupid. Well, this is, I mean, let me just try to examine this process. I was trying to show that, F inverse F satisfy the same condition as T. But I failed at showing that this is symmetric. Why this part doesn't work? Okay, so let's ask. So I was trying to show that, okay, F inverse SF satisfies the same condition, defining condition of T. Okay. T squared equals F transpose F, and T is SPD. Okay? So verifying F inverse as F squares to F transpose F is straightforward. And since F inverse as F is similar to S, they have the same eigenvalues, and hence um, F inverse SF is positive definite. However, if um, if it is also symmetric, but I got stuck trying to show that it is symmetric. You picked the wrong expression for the conjugation. This is, I know this is similarity transform. We want to show that T is F inverse SF, huh? Well, it does work. But T is symmetric, no? Symmetric positive definite. That's the key issue. The uniqueness theorem you're implicitly using, there's a unique, yeah? So here is, it just happens that F inverse SF is symmetric. So this can be used basically because it equals T. Okay. So why does the AI's proof any different? Huh? Because it uses this trick. Okay, it uses a trick that the it multiplies F and then F inverse, and then it square roots on both sides. It square roots on both sides. Left hand side gives you what? Gives you S. Right hand side gives you F FT F inverse, which is the same as T equals F inverse. My goodness. Okay. Huh. Yeah, I guess. Yeah, I was just I couldn't think of about this trick, so that's why I failed. Anyway, this is a pretty difficult question in my opinion. Or it could be just I suck at algebra in general. um, problem two, by the way, problem two from Vizzy's set. Problem two was differential equation, which in my opinion is very straightforward. And problem three was probability. So, which in my opinion is also pretty straightforward. But I struggled big time with that linear algebra problem. Okay, as you can see, I'm still like not fully convinced that I'm able to think about this solution on my own. Anyway, so it turns out that square root was a big weak point in my foundation. I guess good to know. Even after reading Axler's book, I still couldn't think about this solution. And some part turns out to be pretty silly, actually. I mean, it's kind of embarrassing that I couldn't think about that because, yeah, especially when if you just take, yeah, in part three, if you just take where's that? Yeah, part three is down here. If we just take the t to be the square root of f transpose f, you can just verify v equals f t inverse is orthogonal. I guess the SVD method works. Method has its advantage of showing well, of showing part three, but can we do part two using the SVD?
because T is this part, right? Yeah, we can use the SVD to do part 2 as well. We can use the SVD to do part 2. So we're trying to show that F inverse SF is T, right? So F is this U sigma V transpose, that's F. S is U sigma U transpose. F inverse is what? F inverse, well, V is orthogonal, so V inverse is just V sigma transpose. Sigma transpose. Well, sigma transpose, yeah, sigma transpose is sigma. Sigma transpose, because sigma is diagonal. And because F is a square matrix, sigma is a square matrix. And U transpose. Yeah, so this is I, this is I. And what we have here, this should be T. But we have 3 sigma in the middle. It's not quite T, huh? What the hell is going on here? This is F. This is S. This is S inverse. F inverse. F inverse. You see V sigma U trans. Hang on, what's going on? U transpose U canceled, U transpose U canceled, you end up getting V sigma cubed V transpose. And that's not T. T is 1 sigma. What? Someone help me. This is totally bizarre, huh? F inverse SF. This is F. F is U sigma V transpose. Yeah, S is U sigma U transpose. F inverse is, oh, inverse. Oh, this is inverse. Yeah, this is inverse. Then it makes sense. This is indeed T. So the SVD works for part 2 as well. SVD works for part 2 as well. It's just SVD suffers from the difficulty with uniqueness, right? Can we show uniqueness from SVD to show this is unique? Arbitrarily multiplying 1 or adding 0 always be the hardest. Yeah. Yeah, man, you're so right. Yeah, so SVD construction essentially gives you 2 and 3 for free, but not uniqueness. Right? That's the original idea, without using the square root at all. Can we ask ChatGPT how do you do uniqueness with SVD? Okay, so um, so I had the idea of using SVD to solve this problem. Okay, uh, let F be non-singular, show that there exists unique real SPD matrices S and T and orthogonal. matrices U and V such that F equals SU equals VT. Okay. Okay. Um, um, use SVD on F. So F is F is sorry F is U big sigma and V transpose So just take S equals. I mean, there's a letter overloading, so perhaps let's use different letters. Um, we're solving the matrices P and Q, okay? P and Q. SP equals QT. And standard letters for SVD. So take SB, take SB U big sigma U transpose. And P equals U V transpose. Okay, and take V equals, not V, but Q. Take Q equals UV transpose as well. Take Q equals UV transpose as well, and T be big V, big sigma, V transpose. The problem is, how do you show uniqueness? You mean V inverse? Yeah, you're right. Yeah, I figured it out. So basically, yeah, you're right. I figured this part out. So basically, SVD construction gives you 2 and 3 for free, but not the uniqueness part. The problem, the part I got stuck is uniqueness. Once again, the uniqueness is the bane of this question. What do you want to prove? I don't want to do square root anymore. I just want SVD to give me uniqueness. Can we do that? Okay, so let's assume F equals, and here, yeah, once again, you need this uniqueness square root, uniqueness of SPD square root. Okay, you need this uniqueness of the square root. Okay, this is the part where, okay, yeah. So basically the bottom line is, I don't know square roots very well. Okay, I barely think about that, to be honest. So that's why I was trying to show uniqueness using the SVD construction. But the thing is, as we all know, singular value decomposition is not unique, right? And, well, yeah, there's that. Okay. Yeah, so that was last week. I got stuck with the uniqueness and I didn't have the chance to look at 2 and 3.
In my opinion, um, we might as well. I mean, the most economic solution would be, yeah, this one, and just use the uniqueness of the square root to get the uniqueness, and 2 and 3 you get, well, as we just said, follows immediately from the SVD construction. All right, that's it for today. It's getting late, and tomorrow I will start something brand new. Where's that? Hang on, let me just go to the channel, because I mean, the idea is to show that how do you start a new subject from scratch. Basically, that's the note I'm going to go through. So yeah, there's this one. It's this note on rings and field. Okay, yeah. So just so this, I mean, you guys probably already seen my post, because I don't have a formal background in abstract algebra at all. My only education, formal education in algebra, are 2 semester worth of linear algebra. That's it. And so this, whatever abstract algebra I've later encountered in my course, or not course, but research or whatever, or interest, are not systematic. So this node is like 90% new stuff to me. I'm pretty ignorant when it comes to abstract algebra. So I think it's a fair representation of what self-studying mathematics looks like. And yeah, it's like almost like a book. It's 258, right? It's like a short book on abstract algebra, on ring and field theory only. So tomorrow we'll be starting from the basics, okay? And I'm pretty sure I'm gonna struggle much more than I did tonight. But anyway, if you guys are interested, join me tomorrow morning at 8 a.m. Eastern Standard Time. Okay, that's it for tonight, and I'll catch you, well, tomorrow. I mean, right now it's already tomorrow. It's already Saturday here. All right, that'll be it.